I am very happy to introduce Raymond Van thank you, who's the Senior Managing Consultant for IBM Global Services in the Netherlands, who is here thanks to Helen and Cal. He is going to be talking about the Preservation Manager and the Universal Virtual Computer, which are two projects out of IBM's various research offices. This should fit in rather nicely with some of the discussions that at least the faculty have been having at SILS on virtualization tools. So I will turn it right over. Thank you very much.
Thanks.
And there's cake here.
First, I also want to thank Helen and Cal for the opportunity and the kind invitation to visit SILS today and yesterday. I already had some interesting discussions yesterday, and hopefully we have some nice discussions during the talk. I'm not getting out of my rhythm. If somebody has a question, just raise their hands and we can discuss it right away. Hopefully, yesterday my time was a little off and I didn't have enough time, but I condensed it a little bit, so there should be enough time for discussions. I want to talk about SOM, because IBM is doing more than only the research in the Universal Virtual Preservation Manager, but that's where I want to focus on today. And just to give a little background how this whole process and those activities came about, I want to do a little bit of scene setting. In the Netherlands we have the Royal Dutch Library. It's now 200 years old, and already in the mid-90s, early 90s, it started to look for getting ahead and being thought leader in electronic deposit systems. It started to talk with the publishers, Elsevier at that time, and it really wanted to be internationally known and thought leader in the area of digital preservation and electronic deposit systems. They put out a request for proposal, and that's where I came in the picture in IBM Netherlands to build their deposit system. They already had a little bit of experience with some of our content manager software during the 90s. And that's how the partnership on research came about, because they had, of course, a ridiculous question in their requirements for their deposit system. They said, okay, as a vendor, can you guarantee us that in 100 years from now, the object is still available? And not only the bit stream, but really usable, renderable. And of course, IBM being an American firm, that's legally in the contract, that's anyway a big problem, but of course we couldn't guarantee that. And instead we said, okay, we could do a lot of stuff with maintaining the bits, but the rest is ongoing research, and we actually would like to move along that path together with you. And then from the Netherlands we started also to look broader within IBM if there was thinking and some ideas we could reuse. And that's how in the beginning already early Almeida Research also got connected with this project. And then especially Raymond Glory, who is now retired and who is actually the father of the whole UVC idea we're currently further developing. So that's a little bit of the background, and two of the things that came out of there is on the one hand the UVC, and I will show it in more detail in the next slides, to preserve information. And another issue, problem area we identified was the whole management of technical metadata, because we expected it to change over time, technology changes, so you have to include more new technical metadata. In the beginning of 2000, there weren't that many standards on, okay, what should the set look like? And we did research on that also together, and that's where the preservation manager comes into play. So today I want to talk about these two subjects. First, the UVC, and in the second stage of my talk I will focus on the preservation manager. Technology, I think you're all aware, is changing very rapidly, and I just took some milestones out of the history, starting with the ENIAC in the 40s. I think, especially if you're in scientific research, the PDP-11 was a milestone in the 70s all through the 80s. Then came the IBM personal computer, 80s. Then my favorite, because I started studying computer science in 82 at the University of Amsterdam, and I worked on a Gould, the next versions of Unix machine of the PDP-11. And the second year during my study we got the first Macintoshes with a graphical user interface. And up until that time, of course, I was only working on the mid-range and the mainframe computers. So that's the first Macintosh, the 128K machine. So that brings back a little memories. And if you're looking at today, you see it on the one hand, it's getting smaller, and I just took one a small handheld, fully functional XP PC, the OQO, which was released in 2000. And if you go to the other side of the scale and go really big, you have, for instance, the IBM Blue Gene supercomputer initiative, which is for the last 3 or 4 years ranked #1 in the 500 list of supercomputing. So you see a lot in those 60 years change, and of course it's only increasing, and we have to deal with that if we are talking about digital objects and keeping them accessible for the long term. And at the KB, and I always use that also in my talks, long term I say it's okay, it's 100 years from now, that's far enough away, then you have all the challenges. But actually I think you already, for some of the data formats, you already have them in 10 years from now or 20 years. So it's something that's not very far away, it's in the pretty near future. Having said that, I'm coming to the UVC, and the idea initially proposed by Raymond Loewy. We were looking for a way to shield off at least the hardware changes over time and get some stable platform to build up functionality which could help us to keep the digital objects accessible over the long term. And we started to look at a virtual machine. So it's never been implemented in real hardware, it's just a thought exercise, but the requirements we had, it should be very simple. The specification should be very simple, so that if somebody reads the specification, he could easily produce on some future platform a new version of the UVC. And that way we would be able to shield off all hardware implications and start to build on that to provide long-term access for data. We thought it's best to have a very flexible machine, so not let's say a 32 bits one or 64 bits one, but make it bit addressable so you can flexibly emulate any type of program on there, and only give it the most necessary instructions. And actually, if you look at the set, this is already a little bit of an extension, because if you look, for instance, at the logical operations, everybody who had a logical course knows you only need 2 operators for that to implement the whole logic. And the same holds for the numerical instructions. If you can add and you can divide, the other ones are also possible. But that's a little bit, we did some concessions for ease of use. And we came up with 25 instructions. And it isn't said that those instructions are now there forever and we never change them. But our objective is, at least this won't change that frequently. Maybe once in a decade there's a new handy instruction that could be included. But it's a pretty stable base. So I think you see all the normal instruction groups which you need to make useful programs. That's for the information moving in and out of registries into the memory, so the load to store. And we have the sign is implemented as a separate item. So if you want to write back the sign from the registry, there is a load and a store sign. Operations on the registries, you can load information between registries, you can set the signs, you can load constants, and you can inquiry on the length. And all the registries are flexible, it's a virtual machine, so there's never an overflow. We only dynamically extend the register when needed. That's also completely implemented in the current UVC implementation. Then the numerical ones, we have some comparisons operators. Then the branching and the conditional branch, and of course the calling of subroutines. And then I have a later slide that's discussing this a little bit in more detail. Then we have the only interaction with the outside world is provided by the in and out instructions. And that means we are therefore completely cut off from any technology dependencies, because the only way you can communicate is through that channel, that communication channel. And that's shielding off the complete environment. And I think I heard in the faculty there's a lot of interest also in virtualization. We had a look at some of the professional commercial virtual machine implementations that are out there. And what you see is that because it's used for virtualization in the now, in the present, that there are still dependencies over there, which makes it's a good step in the right direction, but it's not right away also a virtualization solution for the long term. Because if you look at VMware, for instance, the change from 5 to 6 makes it that the 5 images are not running anymore, or the 4 images are not running more on the newer virtual machines. So there is still hardware dependency in there. And that's what we tried to get out. The basic instruction set is then built up of the operator, 8 bits. You have identifiers to the segments, which are 32 bits, a flag, and the registers. Because you don't see it that much, but it was a flexible way and easy for us to have actually a machine that's a segmented machine. Because then, for instance, your class or your subroutines, you can nicely put all in their own individual segments with their own registries and their own internal memory. So the whole concept about the UVC is you have segments. Every segment has basically 4 gigas of registries available, because you have 30 bits to identify a registry, and we just place them, we create them on the fly in the UVC emulation. Again, an added value of having just a virtual machine and not being restricted by the physical properties of your hardware. Of course, in the end you are restricted, because if your machine doesn't have any more hardware, for instance memory, then it's getting slower and slower, because okay, you can page a little bit, but there will be a physical limitation in the end. But it's not based on the UVC, it's more based on the hardware below it. So you see the registers, the whole sets with every register has its length. And the register, keep in mind, can grow dynamically so you don't have overflow. And it has a sign. And then you have associated with each segment a bit addressable memory space with it. So that's the basic setting of the UVC. Then the communication, because that's really cutting it completely off from the hardware. It's a very simple communication channel with a very simple protocol on it. On the one hand you have a UVC implementation, and of course at some state it has to communicate to the outside and with the future hardware environment. That's here depicted through the program using the UVC emulator. We also call it in the consecutive slides the restore program. So that's communicated through that communication channel. How you implement that, I basically don't care. You could do it through shared memory. You could do it by running the UVC as a service on another machine and doing it through TCP/IP or service calls. That's up to you. But you have to implement this channel with this behavior, this protocol. Messages are sent back and forth to the UVC in a very simple format. You have a 30 bits type, message type, then a message length and the content. How you use it and how you react at the message types, I will show later. That's something you specify in a logical schema you use with the UVC. So you can define it for your purposes and in different cases differently yourself. So this is the basic structure, and now how are we using this to preserve digital objects for the long term? Actually, because sometimes people refer to the UVC as it's being an emulation, because the UVC is virtual, it's an emulation approach. More correct would be it's actually a combination of both. It's a combination of emulation and migration as we use it. Because take for instance, you have an original object, let's say a JPEG, and there is some encryption in there, and what we say is, okay, in order to interpret that you actually need a program at the moment. Those programs won't be around anymore 100 years from now. Presumably it will also be hard to find the complete specification of JPEG at that stage. So it's better to do something now in the present to be able to get the information out again. And what are we proposing then? Okay, develop a UVC program so that you will be able to run in the future also, because that's developed for that virtual machine. Extract the information out of the JPEG in a technology independent manner. And you have to think a little bit XML-like. It's a tagged system where you specify, for instance, as we did it for images, every pixel by its red, green, and blue colors. But of course, you're not there then, because okay, I have now 3 color numbers, but how maybe RGB is not anymore used the same way as we use it right now. So how do I know what color that actually produces in the end? For that, I say you need to build a logical data view that's completely disconnected from technology. So you have to have a reference point somewhere in the real world. I don't know if any of you is a little bit knowledgeable about color schemes as color management, but you have some color management schemas which are actually experimentally defined, where the color is, you do an experiment and that's then identifying the color range. And basically every coloring scheme that's used, and also with the PC, can be translated to a reference point in that fixed set, experimentally proven color scheme. So you have a 4x4 matrix by which every pixel can uniquely be referenced to a certain color. And you don't need any technology for that. So we push that out by designing a UVC program that takes that JPEG file and generates that logical data view for it. In the end, what you then need is, of course, what I talked about. You need to know how to interpret those tag fields and the information that's in there. So that's the schema you need to know. And one aspect of that schema is also the specification of what type of messages you have defined. For instance, with the logical data view for images, which we now have operational, the pixels and the line information all are different type of messages. So the message ID is already identifying which tag you have, and then the message content is the value for that tag. And in the end, it's our premise is that because that's self-explanatory, and I probably don't, I don't want to do it, but I don't need a machine or a computer to implement that, to interpret that description. I could do it by hand, but then you can in the future build a restore application and render the original image again. But there is also some other flexible opportunities you have, because you can not only render it, you can also probably migrate it to the format that's then used. Or maybe you can translate it to something else completely. So you can rework it and you can have different instances of that same information at that stage. So in the overview, how does this approach works? And this is something we actually also tested out and did for the National Library of the Netherlands. That is, okay, what do I now need to preserve JPEGs, and we did it also for GIFs, in my electronic deposit system. Naturally, I have to store and maintain the digital object. For every instance, in the case of the KB, most of the time, every JPEG or a set of JPEGs for an article are grouped into one AIP in the OAS model. So it's archived as one object in the electronic deposit system. I need to have one copy of the UVC program. The added value is I already have the UVC, the program I write, I can test out now. So I can make sure it's working, and I can test it, and I can use it in the future, because this is really a last resort, as long as there are JPEG viewers available, because it's a slow process. It has to compute a lot, and because it's pushing out every little detail through the communication channel, it's not very quick. So you don't like, you wouldn't like to really view the current images through this solution, but this is being meant as a last resort to access and render the information. So the UVC program I can test today. That's an added value, because if you look at other emulation approaches, they always say, okay, at a certain age, time when the machine is not anymore available, I have to start building an emulator, but at that stage it's hard to test if the emulator you're building is functioning in the same way as the old hardware did. And over here we can test this in the present. That logical data schema, which you need to interpret the information that's coming out of the UVC. And of course a UVC specification. It's better, or you can also store some of the UVC implementations, but in the end I only need the specification. Of course, I only need that once, so I can have 1 million objects, JPEG objects. I only store the UVC program and the logical specification, and the UVC specification once. We currently, the UVC specification is roughly a 30-page document. It's widely available, so anybody could pick it up and build his own UVC specification. And I tested it out now 3 times with a master student, mostly in computer science, and they're all, I didn't tell them anything, I just gave them the document and say, okay, build this UVC according to this specification. And they were all able to do it roughly in 1.5 to a month, 2 months, and then they had a complete correct working UVC. So that's proving to me, because it's not knowledgeable programmers who are doing that, they are still pretty novice at that stage, but they are able in a relatively short time to build the UVC according to the current specification. So that's taking care of, maybe I lose all the UVC implementation I currently have if somebody's picking up the document in the future. I'm pretty confident. Okay, we can't test it, that's the whole problem we're having with presenting approaches and saying, okay, this is making it available in 100 years from now. But I think I'm reasonably comfortable through the experimental results we're having. What do you do? What do you need to do in the future? As I said, we have a future platform, so I have to build a UVC emulator, or maybe there is already one around which you can use at that time. Then I need to build a restore program that uses the logical data view that's being pushed out of the UVC to the external environment, and I have to reinterpret it, either converting it to the new image formats at that time, or just right away rendering it at the devices that are then used, because maybe we have then 3D devices or virtual ones. Who can say what will be the case in 100 years from now? So through the communication channel, the digital object is then loaded on the UVC, and the whole loading and initializing is part of the UVC specification, so that's also clear how to start up the UVC. The object file is loaded, the UVC program is loaded, and it starts to run. At that time, it's pushing out every item sequentially the logical data view, so the information. And with the aid of the logical data schema, I can interpret that information and use it to render the image, in this case the image again. At the KB, we tried this out and use this as a last resort for PDFs, where we said, okay, we convert the PDFs to JPEG images, and those will be available for the long term through the UVC mechanism. We also did earlier a proof of concept with PDF, because actually you could also say, okay, why don't you use the logic and the application of the PDF itself and make a UVC program for the PDF right away. Then I don't need that intermediate step. But the functionality, the richness of the functionality in the PDF was a little too great to just do that quick and easily. For instance, and I talked a few times a little bit about it with some people of Adobe. Adobe could easily do that because they have the source code for it. So what we are looking for also, and I think that's also an important aspect, all of these solutions, and I think that's true for all solutions for long-term preservation, shouldn't actually be proprietary. We are working also from IBM to push this into the open domain and make it widely available, because it shouldn't be dependent on one organization to provide and maintain this for the long term. There's also a side effect, which is also very nice. You could also use it to check your migration automatically. Probably at a certain point, for instance, the KB has now roughly 8 million PDFs in its archive. And at a certain stage, maybe 50 years from now, that probably has to be migrated to something else. So you're talking at that stage maybe about 20 million, 30 million objects that have to be migrated. Of course, you can't check anymore manually if you were successful in all cases. You actually would like to do that in an automatic way. The UVC through the LDV is giving you some opportunity to do that, because I could say, okay, let's take our TIFFs, and they take up a lot of storage, so maybe not even from a preservation perspective, but more from an space optimization perspective. I want to convert them into JPEG 2000. I'm doing the process. I can build a UVC decoder program for both the JPEG and the TIFF. And of course, actually the machine independent specification we have, it's not biased to any format specification for images, so it's generic in that sense. So they should produce the same kind of output, and that can easily be compared. So that's giving you then a mechanism through converting it to that intermediate format, that LDV format, to check automatically whether your conversion maintained all the information. We always, and that's something I learned from the KB, always start small and then think big. So the previous example what you saw was what we call data preservation. You do that for stable formats with not much logic, like Word documents, images, also a little bit dynamic but still static from an analysis perspective, sound, video, you can all specify it in a static way. Of course, there are also situations where you really need to have the program. And we always kept that in mind, because we always said the UVC should actually be used in a wide range of circumstances. So we have also a setup which we call the UVC program emulation. And to show that a little bit, I have 3 examples. For instance, the first one is BPM, and there isn't actually any processing logic in it. It's just as a TIFF, it's the raw data. So if you have the metadata description of how to interpret that data, you basically have all the information you need. So in the end, to build in the future a restore program, I actually don't need the UVC. I need to have the metadata description, and then I could probably right away write a new viewer at that stage. And we talked about the JPEG example. There is compression algorithms in there, so there is logic that's presented by the process part. So that part you actually want to move into the UVC, because that's now stable and you don't need the application anymore. So that's the example I just discussed. That's the data preservation scenario. In Planets, and that's a 6th European Union funded project where we're also involved from IBM, we're going now to the next step, which is termed program emulation, where we take an open source Excel spreadsheet program. We take out all the peripheral dependencies in that program. We establish a schema for interacting with the spreadsheet application through the communication channel, and then recompiled, because we have the source code of that spreadsheet, we recompiled the spreadsheet for the UVC. So now the spreadsheet program is running on the UVC. We have identified how the protocol looks like over the communication channel, how to interact and update cells, how to change formulas in there. And then you can interact with the spreadsheet through the UVC. So now I've made some of the logic, the program logic, available for the long term by using the UVC. A next step could be, and then you're coming actually into full-fledged emulation, The KB itself is also working on Diascuri. It's a portable emulation environment. And in the end what they're saying is, okay, we built portable components for different hardware, and you can configure a new machine with that. Let's say this ThinkPad, this T61, or another machine, and then you can run your programs on that one. What you could do with the UVC is actually have, where's the problem? The problem is in the device dependencies and the drivers for the devices you're using. If you extract that away to a core UVC program, and you have to re-implement that in the future for the then common devices, you can run the rest of the emulator on the UVC stack. So that's then maintained also and accessible for the long term. And the only thing you have to do is build, connect it to the future environment through re-implementing the device drivers at the new future environment. So that's the next step. But this one is already, you can do that very quickly. We have at the moment almost a complete Java compiler for the UVC. So as a format provider also, you have your source code from your application. If you look at it and you take out the device dependencies, you could easily, without much effort, build a version of your application for the UVC, which would be long-term preserved. And that's what we're actually trying to promote, because it's not the objective of the KB of IBM to build all those decoders. Actually, I think we want to move into a situation where format providers and applications for those format providers build these type of last resort solutions themselves. So that's one part, that's the work we're doing in the area of the UVC. Now on to the preservation manager. When we started, and keep in mind that this was now 8 years ago, so I think we made a lot of progress during that time, and I think the KB was involved also in a lot of the progress during that time. Nowadays you have METs and you have all kinds of metadata schemes, especially for maintaining technical metadata. With technical metadata, I mean the data you need to describe the hardware and software environment you need to render your digital object. In 2000 we weren't that far yet, and we thought about it together and thought, okay, actually what we need is a flexible way to specify technical metadata for different type of objects. Because we don't know, and I actually do not believe there is one type of schema where you can say this fits all the digital objects and all the purposes. There will be differences. For instance, the KB did some experience with PDFs because 8 million PDFs are in there. And you see that there's a lot of implied dependencies with fonts it expected to have on its operating system. If you're not aware of that, the PDF won't render correctly. So that's some technical meta. In that case, you actually want to register the font dependencies in the PDFs you're ingesting. So we thought of a solution. Okay, what can we do to manage this in a structured manner and also get the most benefit out of it? And that's how the preservation manager came about. And we actually envision for that 3 purposes. One is to identify the digital objects and digital not becoming accessible anymore. So it has to signal, for instance, if Windows 95 is not anymore available, what's the impact on my digital objects in my collection? Do I have to do things for it? The other is then analyze that technical metadata to see what's the approach I want to take. Do I need to emulate stuff? Can I migrate the digital object? What's the action I want to take? Because again, there is no single solution for every object or for every case. I think it has to be analyzed on a case-by-case basis or on a collection basis. And what some people forget, but I think it's also important, that you give people guidelines, especially for complex objects which need programs to be installed on your machine. Give guidelines what the environment should look like and able to work with that type of digital object. So it's not only for the future, it's also part for the present, for just providing access to the information. And what we came up with, and it's a very often used approach in computer science, is if you look at it, you can see a type of layering model, and Tannenbaum, for instance, in structured computer architecture also has those. And if you look like it, at a very high level, you can actually roughly identify 4 layers. You have your data format, which has to be specified. So it's providing meaning to the bit stream and structure to the bit stream. You have your rendering application, which uses that data file and starts to render it. You have all kinds of shared functionality, like your device dependencies, your file interaction, you're working with your screen, which is provided by your operating system. And you have your hardware below that. Because some of the objects could need specialized hardware. For instance, certain games need a certain quality type of graphical card in there, otherwise it wouldn't perform. That's the type of hardware dependencies you're looking at. This is the global view. Of course, depending on what type of objects you're looking for, this could actually be 6 layers, because just as I mentioned with the PDFs where there's font dependencies, I probably want to include between here a layer specifying the fonts I need. If you look at the UVC approach, how I would represent that, I actually am not anymore bothered with the operating system and the reference platform, because if we look back at the UVC, the only thing I need is I need to know which was the UVC specification I used. I need to know the LDS schema I am using and what decoder. That's the only 3 layers I see over there. So you see, there are different, depending on the type of objects and your functions, there are different ways of splitting this up into more or less layers. And that's a little bit we took as the basis for our preservation manager and starting to work on. We connected that with the concept of view paths. And view paths are actually specifying hardware and software stacks which are valid options to render a particular object. So here we have PDF version 7. And of course we have a window Acrobat reader. That's running on Windows 95, XP and Vista. It's running on multiple hardware platforms. You probably we also have an AIX Acrobat version, running on different operating systems and on different hardware. If you describe these different view paths, you can also do analysis. So I can say, okay, what if Windows 95 get obsolete? You immediately see there's a view path now not anymore accessible. So I'm limited in the number of ways I can render my PDF. You could go a step further and say, okay, AIX, the support for Acrobat Reader on AIX is also closed. So that means this whole view path, this whole tree side is gone. So now you basically actually left with one operational view path. We don't expect all the possible view paths to be specified in the preservation manager, What you could do, depending on the importance of your collection, you could say, I always want to have 3 separate active view paths for this collection. And as soon as some of those view paths get inaccessible, you have to decide on how to bring it up to the level again you require. So it's not meant to be a complete specification of all the possibilities. It's your mainstream possibilities you think are the ones that have to be maintained. And if there's one left out because certain components in the technology stack are obsolete, you have to see how I can bring it up to the right level again. That's exactly where the preservation manager comes into play. It has 2 parts. It has a model view, which defines the file formats, defines what we call the preservation layer models. That's a template identifying how many layers and what the information in every layer should be. And then the actual view path, which is then, according to a certain template, the actual technical metadata which you associate with it. So this is the definition part. On the usage part, we have then a browse view, where you can browse through all the technical metadata that's being maintained in the preservation manager. You can also look at the recursive closure, and what do I mean with that? For instance, everything, and that's coming into the later slides, is built on the elementary building block and attributes. First you define attributes, then layers, which are sets of attributes you cluster into one layer, and then PLMs by selecting multiple layers. If you say, click for instance on an attribute, then you can see through the closure which layers all include that attribute, which of those layers are used by which PLMs, and which view paths are being defined including that attribute. So that's, and I will show it, I have a picture on that later on. First, how do we build it? And I skipped two steps. It's what I call, you build your PLMs Lego style. So, as I said, you see here the 3 components that you use to build, first of all, a preservation layer model, that you have to define attributes. Attributes you can flexibly cluster into layers. So, for instance, I would like to define an operating system layer, and in the operating system I have the name of the operating system, potentially a version number as an attribute, the supplier, the vendor of the operating system, and some additional information. I can flexibly define that. It also means that I can reuse different layers and attributes in the creation for different PLM structures. So everything is being focused on reuse, and because of the importance, it's also so that all the information once defined is never being deleted. So if a view path is not anymore accessible, it's being identified as being obsolete, but the information will still be kept in the preservation manager. Because from an archaeologist, I never can pronounce that that word. But maybe in the future you want to analyze the technical metadata to see if you can rebuild the environment. Here we come in, this is the example where we come in and say, okay, I have different layers specified, they are all listed in here, and I now want to build a new PLM layer. So I have to decide which layers become part of this PLM structure, and in this case it's a disk image layer, because the KB for all its CD-ROMs, what it currently does is it's installing the CD-ROM on a reference workstation. It's then extracting a disk image from it, and that's stored in the archive. And that's their best effort where they say, okay, hopefully in the future we're able to emulate that machine, and then you can reload the image on that emulator. So that's their way of thinking to preserve it for the future. So I need to identify, okay, what type of version of disk image application is used, and I have just a basic hardware layer describing the hardware that's needed for that. So at this stage we have defined the attributes, the layers, and we are building PLMs. And here you see some of the PLMs that are identified in this example. For some objects, they don't require any other special things, so you could say, if I know what the OS is and the application, that's fine, that's enough for me. In other cases, we have graphical dependencies, so I would like to have some layer describing the graphical requirements for that solution. And as I said, we have also a PLM, for instance, for the UVC approach. So this is a flexible way to deal with technical metadata, but still manage it and define it in a structured way. So we have the PLMs. Next step is, okay, I want to relate renderable solutions, so hardware-software combinations to a file type. So here, sorry, I have to go one step back. First, you have to define view paths. So the real technical metadata according to a selected template I have. So, okay, I say I want to define a new view path. It's the deployment set. That's the software for that disk image. I say I take the basic OS dependent PLM as the template. Then it automatically gives all the attributes I have to fill in, and then I can fill in the different information, the different technical metadata associated with it. So now I have a view path. Next step is the association with file types. So on the left I have all the file types that are currently being ingested at the KB. It's a little bit over 30, but there are some obsolete ones in there and some ones that aren't correctly defined. So we have to clean it up a little bit. So you have your view, you have your file type over here, and now you can say, okay, here we have the technical metadata, the view paths, the rendering solutions, which we already defined, and you can now select which ones are able to render that file format. And we can also grade them. You could say this is a good fit, this is completely supporting the whole functionality of the format. Or for instance, if we look back at the UVC, that would probably be labeled as a low option for a view path. It will give you the information, but it's not the nicest way to do it. In the new version, because this is all the pilot version, we're currently working on really officially releasing the first official version of the Preservation Manager, and that should be out somewhere in the middle of March, and then this becomes more flexible, and every organization can define its own labels it wants to use. This was just a placeholder. I don't think you need 10 labels, but maybe a little bit more than 3 to typify the match. We have also some quality control in place. And, wait a minute. You see every time over here you see a status of objects and the quality process, and that's the same. I've here the example of an attribute, but the same holds for layers and PLMs. You can first be in a working environment, so it's under construction, you're just defining things, testing it out, and at a certain point you're saying, okay, this looks okay, I want to release this. And then you say, okay, I want to propose it to be defined, and defined means it can really be used in the deposit system to specify the technical metadata, for instance in the case of PLM, or the view path is really used and known in the deposit system. It can either be rejected, so there's a quality gate over there. Then it comes, when it's approved, it gets a status defined and then it can be used. At that stage, when it's not active yet, it can still be deleted because nobody is using it yet. It's known there, but nobody uses it to associate it to a file type. Once a view path is associated with a file type, it's active. And that's actually an end state. The only thing that can happen with a view path, the attributes can never be deleted at that stage. In the case of a view path, there is one additional transition you can have, and it's going to be obsolete. But it will still be in the deposit, in the preservation manager. So all the data, it's only modified by addition, nothing is thrown out. And once defined, you can't change things anymore, so you can't update the values anymore. That's another quality aspect. Over here then, the simple, and we are extending this a little bit in the official version. With what I talked about the recursive closure, I selected over here a certain PLM. Then I right away see the layers that are included in that PLM. The attributes that are associated with that layer, and on the other side I see all the view paths that have been defined with that PLM and all the file types that are associated with those view paths. So that's how you can do analysis then, because you could say, for instance, okay, I click on a file type and then right away I see how many view paths are associated with them. Then I can look in the values of the attributes and do what if type scenarios. What if Windows 95 is not anymore a viable option? What's the impact on my deposit or on my file formats? This is the final slide. What do we see as usage scenarios? On the one hand, it's for file type management and technical metadata management, but you could also use it as a file or software registry as an independent solution. What are our plans within IBM? We saw that within the KB, and this is very computer science oriented, so it's hard for the KB to fill the preservation manager with real life data. They're getting better at it, but it's a skilled, and you have to have a lot of background in computer science. So what we are thinking about from IBM is building, at least for our own software, because you have to to do what you preach. For our own software, build those view paths and those specifications, so that people have an information site where they can see, okay, can I still do something with this Lotus 123 or whatever kind of software package? That's one aspect. The other is, of course, then we can also warn people and signal people, hey, watch it, this is not anymore a viable solution. You have to take action. And on the other hand, and I didn't talk about, the other aspect is then, because we have this wealth of technical metadata, you can also advise people on what to do. So you can have advisory services, whether to migrate or to emulate information. So that's the next step, because we, in the end, probably will see that the whole aspect of technical metadata management is being done in some specialized organizations, and not everybody wants to deal with that. They rather have a subscription and say, okay, I have PDFs in my deposit system. You give me a signal when I have to do something and give me an advice on how to do it. Okay, that's the end of the talk. Here are some of the links which might be of interest. The top ones are related to the UVC, the KB and Coppola environment, because this is all part of our VIA solution, the electronic deposit system we developed for the KB and also for the German library. This is something I didn't talk about, but we are also into the next generation of storage devices which are more preservation aware, so that more functionality is right away getting into the storage devices itself to help you. Okay, thank you. Any questions? Yeah?
So I guess one of the things that comes to mind is that it seems like a lot of the work here is focused on people as the consumers. You did mention a few parts where a machine might be actually pulling the data out of some of these tools. So I guess my question is, I'm a text miner, and so just getting the text out of the PDF document would be really helpful to me. Not the bits, but the actual, knowing that it's a greater than sign, for example, would be helpful. So I guess, do you partner with people who are interested in that side of things in order to test the futuristic piece of this work, or how does that fit?
It depends a little bit, because I mentioned it's a last resort solution, so performance isn't the main focus in the case of the UVC. I think, as far as I understand you correctly, what you're looking for is mere what we call characterization services, where you say, okay, it's not from a preservation perspective, but I actually want to have services I can dynamically put in my ingestion stream, for instance, for the electronic deposit system, and extract the text out of the PDF, for instance, to index it. That's also, it's another subject we talked a little bit about yesterday. You see that also more and more coming, and especially the whole setting of service orientation provides an open-ended environment where you can say later on, okay, I need a certain service, okay, this vendor is providing me with that, okay, I'll link it into my whole process dynamically on the fly. So I think if that's your focus, really to use it now and to provide better access, then I would say it's a characterization service you're looking for, and it's not as much as the preservation aspect. So you probably wouldn't use the UVC for that one, but some performing characterization service, and they are there.